Para, what is that? Omega, what is that? Kilo, what is that? Centi, milli, micro, nano, pico. Those you should memorize. And those are definitions of the metric prefixes. The only other definition that you had was what? Well, you have some others. I don't know, is this chemistry or not chemistry? How many, do you know how many feet there are in a mile? 5,280. There, and is that by definition or by measurement? That's by definition. So the only other odd one is the 2.54 centimeters per inch.
You won't need to know like atmosphere definition or anything like that, right?
Well, there are atmosphere definitions.
Yeah, I think 1 atmosphere was 14 or whatever it was. Like, we need to know that.
That's not a definition. 1 atmosphere is 14.7 psi.
Yeah.
It's not a definition. Because, well, if you're ever uncertain about what is a definition, what is not a definition, do a conversion here. Like, for example, if I went from atmospheres to psi. Oops, actually you can't see this here. Let me show you here. Does it come on or not? Yeah. I mean, it's still useful to know this, but since it's not a definition, then I'm not going to have you memorize it because, like for example, there's a number. What was that number I was talking about the other day? For example, I don't want you to memorize 1 pound is equal to 2.2 kilograms, or is it 2.2 pounds per kilogram? Or is it 2.20, or is it 2.205? It's none of those. It's none of those because that's those are just, rounded numbers to a certain number of sig figs. And then you get to the point where it depends on what class. You remember I told you I don't want you to relearn something? Well, one of the numbers that you're supposed to memorize in Chem 4 is we'll talk about this later, but they have you memorize 0.861. And then, okay, so you finally memorize 0.80861. And then you get to Chem 1A and I tell you, no, 0.0861 is not going to cut it in this class. You need to memorize 0.08602, or something like that. And so, for sure, the definitions aren't going to change, and how you memorize the numbers depends on how precise your answers are, and it could depend on the level of class. So for us, heck, I might say, okay, you memorize that 1 atmosphere is 15 psi. In the next class you go, oh, 15 psi, that's not going to cut it. We've got to be more precise than that. I want you to memorize it to 14.7. Okay, you memorize it to 14.7. Next class he comes along, no, we need 4 sig figs at least in all our calculations. So then you got to memorize it to 14.70, and then, And so, anyway, a definition though is a lot easier to memorize, and it's not going to change. So this is why I said memorize the definitions. Now, what is a definition? This is not a definition because the number of digits just keeps going. It's like pi. Well, everybody's memorized pi. Some people memorize pi as 3. Some people memorize it as 3.1. Well, I think most people memorize it to 3.14. But what if you need 4 sig figs? If you need 4 sig figs in your calculation, 3.14 won't cut it. Unless, of course, it would definition. If it were definition, like 1 inch is 2.54 centimeters, then you know it to infinite sig figs. So how many definitions were there? The metric prefixes and 1 inch is equal to 2.54 centimeters, and those are the only ones that I asked to memorize. right? Except for some other ones, like, the other definition, well, did you encounter other definitions? There were. 1 milliliter is defined as 1 cubic centimeter. That's it by definition. Okay. There's some other definitions. 1 atmosphere is 760 millimeters of mercury. Okay. 1 millimeter of mercury is 1 torr. Those would be examples of definitions, because if I did that here, I'm going to go from atmospheres to millimeters of mercury, or torr. Torr is slightly different. Well, anyway, we do it. And so just focus on those. This is on. Okay, other questions? You guys are going to have a lot of memorization in chapter 6 to do. And so things like liters to gallons or gallons to liters, don't worry about those. Those are typically given. Others, I would be tempted to give you 5,280 feet per mile, unless you learned that in elementary school. Maybe you did, maybe you didn't. All right. Well, anyway, talking about nomenclature. Excuse me. You will have to memorize a lot of stuff in nomenclature, and some of the stuff isn't so clear. Some of it's a little ambiguous. And so let's talk about naming elements first. When somebody's talking about hydrogen, like the element hydrogen, they could be referring to different things, So if somebody just says hydrogen, let's say elements. Somebody's just talking hydrogen. What would pop into your mind? Well, for most people, when somebody says hydrogen, they would think hydrogen is a gas that occurs as a diatomic molecule. In other words, when somebody thinks of hydrogen, they think H2. But they might be referring to something else. Like, say, for example, I asked you, how much hydrogen is in water? Well, water consists of hydrogen and oxygen in a ratio of 2 to 1. And so there are going to be 2 hydrogen atoms for every oxygen. And so if I were to ask you how much hydrogen, which are the white ones here, how much hydrogen in water, you see there's 2 hydrogens for every oxygen, so there are 2 hydrogens in water. In other words, when I'm asking you about the hydrogen content of water, would you say the hydrogen content of water is H2? There's 2 hydrogens for every oxygen? Or would you say, just say hydrogen in water? Because it's H2O after all, water is H2O. And so that means there's an H2 in water. But when we think about H2 is a flammable gas. Does that mean water, has some kind of storage compartment there which contains H2 gas? No, in fact, when we look at water and compare the structure here, the hydrogens aren't even bonded to each other. In H2 gas, they're bonded to each other. The bond is quite strong. These bonds are actually electrical in nature, positive and negative attractions, but it's hard to see here, so we'll talk about them later. But these hydrogens are actually bonded to the oxygen. And so when I look at H2O, does that mean there's one hydrogen molecule and half an oxygen molecule? No, it means that, we have hydrogen and oxygen in a ratio of 2 H's to 1 O. And so when we talk about hydrogen and water, we talk about H atoms rather than H2 molecules. And so what we say is, okay, there are 2 hydrogen atoms for every oxygen atom. Water. That's how much hydrogen is in water. 2 hydrogens for every oxygen. And so that brings up a problem with nomenclature, and that is when somebody's talking about hydrogen water or hydrogen gas, they use the same name. It's hydrogen. And so it's a little bit ambiguous. When somebody's talking about hydrogen, are they talking about hydrogen that's inside the compound? Or are they talking about hydrogen, the standalone element? Even if they're talking about hydrogen, the standalone element, what you can do is you can break these molecules. Basically these are electrical forces holding these 2 atoms together, but if there's a severe collision, or if you use some other means, you can break apart the atoms. And when you break apart the atoms, then you got what we call hydrogen. And so hydrogen could be H2 or it could be H. Normally we think of H2 because H2 is the stable form, right? And H is less stable, but H could exist as well. And so what we have to do is we have to be a little bit more descriptive. And so in order to, it's a little ambiguous. Here, hydrogen and water is H2O, but, if we had hydrogen gas, then we know, okay, clearly it's something different. Hydrogen, we call it gas. Hydrogen gas would be H2, well, that's what they say there, but what about H? Would H be a gas too? So hydrogen gas could be H2 gas, or it could be H gas. If we break apart the molecules. But normally when we're thinking about hydrogen gas, we usually pick the most stable form. This is more stable. Associated with that. And so we come up with different names. To be clear, we would call H2 different names. For example, we call this diatomic hydrogen. If we just use diatomic hydrogen, then it's very clear. Well, that must be H2, diatomic 2 atoms hydrogen. Or we call this elemental hydrogen. When we talk about elemental hydrogen, or hydrogen as an element, we're looking for the most stable form. The most stable form is H2. They like to pair up. If you break them apart, they become unhappy and more reactive. And so this would be elemental hydrogen. Or we call it molecular hydrogen. Molecular hydrogen because it forms molecules rather than atoms. And then H, all these are hydrogen. Or it can be called hydrogen. And the same thing with H, it can be called hydrogen. So to clear things up, we would call this atomic hydrogen versus molecular hydrogen. It's hydrogen that occurs in the form of just atoms. This could be gaseous too. So we could have atomic hydrogen in the gaseous state as well. Atomic hydrogen. Or just hydrogen. It need not be gaseous because in liquid water, the hydrogens are bonded to oxygens in the form of liquid. And so it becomes a little bit ambiguous. And the same thing with oxygen. When we talk about oxygen, the first thing that comes to mind is O2. But if I were to ask you how much oxygen is in water, am I talking about O2? No, not at all. I'm talking about atomic oxygen. Even though I don't want to say atomic oxygen because it's too much work, I'd rather just say how much oxygen is in water. And then, what is the oxygen in this room? And I would expect you to know, oxygen in this room is O2. The oxygen in water is O. if some hydrogen leaked into this room, then hydrogen and oxygen make a pretty unstable combination. But and so that means, when we're naming elements, sometimes it's a little ambiguous, and sometimes we need to add a little bit more to the name to make it clear what we're talking about. All right, this is an example of a chemical separation. What they have here is, and this is in your book, they have an electrolysis apparatus in which they pass an electric current through here, apply voltage. So they're taking water and they're separating out water into hydrogen and oxygen.
For the name, would that be different from like the dihydrogen monoxide? Like different? Like atomic oxygen would be the same as monoxide? That would be.
Well, these are just the name of the elements. If you get into something like dihydrogen monoxide, DHMO. Have you heard of DHMO? Yeah, DHMO. DHMO, that's a compound. And like water is a compound. It's not an element, so it's two or more elements chemically combined. And so we have a different naming system for that. And so if we're dealing with elements are just going to be pure, hydrogen, pure oxygen. That's it, not combined with anything else. But I'm talking about this because compounds are made up of the elements. So when we name the elements inside a compound, how do we do it? And how do we express it? Okay, how we do it is this. Even though when I'm thinking about the element hydrogen, I think of H2. When I think of the element oxygen, I think of O2. But when I'm thinking about water, I'm thinking not about H2. I'm not thinking about O2. I'm thinking about H and O. When water gets split apart, you think, okay, when water gets split apart, we split it up into H and O. We think we'd split it up into atomic hydrogen and atomic oxygen. However, those are the unstable forms. They're unhappy when they're not paired up. And so even though, I'd like to split this up into atoms of oxygen and atoms of hydrogen, they don't. They end up pairing up and going into H2 and O2. And so this is the electrolysis apparatus here. Actually, I tried to set this up, but it didn't quite work. And so we have some batteries here. The electrodes are just some metal conductor, in this case platinum. And when we hook up the power supply like this, what happens is the batteries will suck electrons out from this metal, which makes it more positive, and force electrons onto this electrode. Electrons being negatively charged. And so we build up some static electricity here. If we build up enough static electricity, we'll generate a high enough voltage. And we don't get a lightning bolt here. What happens is we'll start to break apart the water molecules. That will be electrolysis there. All right, so let's take a look at some other elements here. This is the element sodium here. What do you think of when you think of sodium? Well, I think of sodium metal. Sodium metals like this. Does sodium metal form molecules? No. Sodium metal, what's this called here? Crystalline lattice. Sodium metal forms a metal lattice like this, in which we have a whole bunch of sodium. Would this be considered a gigantic molecule? No. It's not considered a molecule because a molecule would have a definite end to this. Sodium doesn't have a definite end. Sodium just can continue going on in 3 dimensions. And so look at this huge chunk of sodium here. It just keeps going on. Right? Whereas something that would form discrete molecules would have an end. So for example, chlorine. This is chlorine here. Chlorine's a green gas. Sodium's a silver metal. Chlorine, this green gas, we start off with 1 chlorine, we go to 2 chlorine, and then it stops there. That's a diatomic molecule, not a triatomic. It doesn't want to continue. It stops at a diatomic molecule. And these are discrete units. They're stable. Chlorine happens to be a gas, so they're separated. Sodium's a solid, so we get this ladder. And so that's elemental sodium. Now, when I'm talking about sodium chloride contains sodium and chlorine. The chlorine that's contained in sodium chloride is the chlorine that's contained in sodium chloride chlorine gas, the green gas? No. And so when you take sodium and chlorine, they combust like that. And that's what you see in the middle flaps there. They're combusting together. We'll talk more about chemical reactions later. And we form sodium chloride. Here's a few crystals of sodium chloride. Sodium chloride, is this a molecule of sodium chloride here? Is that a molecule of sodium chloride? No, because the crystals can be big or small. People try to make huge salt crystals. Huge salt crystals, they just keep growing bigger and bigger. And so there's no definitive end here. This is what we call a compound, but well, water is a compound too. There's a different, this is what we call the structural wise. We don't call these molecules, we call this a lattice. A crystalline lattice is what it is. And so when we talk about sodium chloride, how many sodiums are there? There are lots. And so let's count them. 1, 2, 3, 4, 5, 6, 7. So should we count all the sodiums? And then count all the, no. It doesn't take too long. And so what we do for this is we just take the simplest unit. The simplest unit would be 1 sodium and 1 chloride. And so we see it's a 1-to-1 ratio. Even if we counted all of them, it's going to come out as a 1-to-1 ratio of sodium chlorine. And so sodium chloride is known as table salt or NaCl. And when we think about the chlorine content of NaCl, we're not visualizing this, we're visualizing these individual atoms. Those are charged atoms. Do you know what charged atoms are called? Ions. So that brings up another thing that's ambiguous. This is called sodium, right? And this is called sodium. And they're different. And so sometimes we like to qualify it. So the first sodium, sometimes we'll call it sodium metal, And the second sodium, do you know what sometimes we'll call it? We won't just call it sodium, we'd call it sodium ion to indicate it's charged sodium versus neutral sodium. Neutral sodium would be sodium metal. All right, let's go back. These figures aren't in the PowerPoint in this book. So that's just a little bit about the nomenclature of elements. All right. So nomenclature also involves writing formulas. So let's take a look at writing some formulas based on this. This is a carbon here, the black one. This is oxygen. So this is CO. Is this a molecule or a lattice? A molecule. Because it doesn't extend. There's one carbon, one oxygen, stops. So this is what we call a carbon monoxide molecule, CO. What is this? This is a carbon here, and this is carbon dioxide. We have 2 oxygens, 1 carbon. Do you know what this is? The white is hydrogen. The black is carbon, so this would be CH4. CH4, do you know the name of that? Methane. Okay, now the way we do this is this. We have a C with 3 H's, so we call that CH3, and then O, and then H. So this would be CH3OH would be the formula. CH3OH is what we call a condensed structural formula because there are 2 ways of writing that particular formula. So CH3OH is called the condensed structural formula. And so if we take the structure and condense it into a formula, this is what we get. This we can compare with something called the molecular formula. The molecular formula would look like this. It'd be CH4O. And so what's the difference between the molecular formula and condensed structural formula?
CH3OH shows you the structure, and the molecular formula is just the shape.
Just the different elements in their number corresponding to the rest of the reaction.
Yeah, that's it. You know, the molecular formula just tells us the composition. The condensed structural formula tells us the composition and the structure, or at least a little bit of the structure. You know? Because yeah, just based on this, we know how things are attached together, and then we've got to figure out what it looks like structurally, and so we would need a little bit more information to do that. Do you know what this last one's called, CH3OH? Whenever we have this COH, if we have a COH, that's a special group, and it's called an alcohol. All alcohols will have a COH group incorporated in it. This one is called methanol. Meth, do you know what meth refers to? Meth refers to one carbon. And so when I have something like methanol, this is a one carbon alcohol. When I look at this, I can't really tell. Is that an alcohol or what is that? Is that a COH type group? You know, sometimes it's hard to tell. You have to really figure out what the structure is. How about this? Number 8, does that look like a alcohol to you? Does it have a COH type group on there? It does. Right here, there's a carbon OH. It's a little bit more complicated because we've got to look for other groups as well, but this is an alcohol. Except rather than having one carbon, it has two carbon. Do you know what two carbons is called? When you have two carbons, we don't use meth, we use F. And so this one is called ethanol, which is a two-carbon alcohol. They're common names as well. Ethanol is often called grain alcohol. Methanol is called wood alcohol. Can you get drunk off methanol? No. Would you want to try it? No, you wouldn't want to try it. You wouldn't want to try it because you could go blind if you try it. Is that true, or is that just some kind of urban myth? Is that urban myth? You could go blind drinking methanol? Yeah, it's true. It's true. In South America, actually, you don't read much about it in regular newspapers, but in the chemistry journals, every year people go blind and people die from drinking methanol. Methanol is called wood alcohol, so we don't want to. And so just an extra carbon makes a huge difference because at least ethanol, you aren't going to go. Well, I mean, you could still die drinking ethanol, but you know, in small quantities and stuff. And so just an extra carbon, basically. But what's the formula for ethanol? It's C. Well, we're not going to do C2. We're going to do the condensed structural formula. So we're going to add it by atom. It would be CH3. Okay. So ethanol is going to be CH3. And then the next carbon is going to be a C with how many H's? 2 H's. So it would be a CH2. And then we have an OH stuck on that. And so this would be the condensed structural formula for ethanol. The molecular formula is going to look different. The molecular formula would be C2H6O. That would be the molecular formula for ethanol. Molecular formula for ethanol just tells us the composition. There's a problem with the molecular formula for ethanol. And the problem with the molecular formula for ethanol is a problem of what did we have? We had isotopes. Isotopes were what? Different masses, same element. Isotopes. Well, we have another problem. That problem is going to be isomers. Have you heard of isomers? Isomers are the same molecular formula, different structure. And so, if I have a formula like this, C2H6O, I don't know if that's an alcohol. Because what am I looking for in an alcohol? In an alcohol, I should have the COH group. But there's another way to arrange these atoms. Take a look at B here. B, what's the structural formula for B? Structural formula for B is going to be CH. How many hydrogens? There's 3. The third one's hidden. You can't see it, but you get a peek there at this one. And so CH3O. CH3. Is this an alcohol? This is not an alcohol because this has a COC versus a COH. When we have a COC, do you know what we call those? We call those ethers. And this ether is called dimethyl ether. What is the molecular formula for dimethyl ether? It'd be, C2H6O. C2H6O. So, when I see a formula like this, I don't know, is that ethanol or is that dimethyl ether? Or maybe it's some other isomer. I don't know. Dimethyl ether, do you want to drink this? Let's say you ran out. I ran out of alcohol. I'm going to start drinking dimethyl ether. You want to drink that? No. You don't want to start drinking dimethyl ether. You might consider drinking dihydrogen monoxide, though. If you consider drinking dihydrogen monoxide, DHMO, you might be okay. As I just mentioned earlier. Dimethyl ether and ethanol have even though the composition is exactly the same, they have different properties because of different structure. So structure is so important. When we have a link like this, a link like carbon with an oxygen, we call this a ketone. This is a 1-carbon ketone, so this one's called methanone. Methanone's kind of an awkward name. You probably haven't heard of methanone so much, but this one has a common name. The common name for this ketone is not methanone, but it's well, actually, this is not a ketone. Sorry, this is a different group. This has an OCH. Which is a little different. In other words, what is the formula for this one? H2CO. H2CO or CH2O, either one. So if we're looking at CH2O, this one's kind of weird because this is what we call an aldehyde. And this one is a 1-carbon aldehyde called methanal. Methanal has a common name. The common name for methanal is formaldehyde. So this is formaldehyde. This is a ketone, sorry. This ketone, the structure is a little different here. This is not an aldehyde because for an aldehyde, we need a hydrogen bond to this carbon. These are little structural differences. These little structural differences make a difference in the properties. And so this is an aldehyde because this carbon has hydrogen bonded, actually 2 hydrogens. But when we look at this carbon here that's stuck in the center, there's no hydrogens bonded to it. And what's the structural formula for this? The next structural formula would be C, H1, H2, and then there's an H hidden right there. The CH3, COCH3. This is 3 carbons, ketone. 3 carbons, do you know? 1 carbon they call meth, 2 carbons they call F. Do you know what they call 3 carbons? Prop. And so this one is called propanone, or more commonly known as, someone know what the common name for this is? This is acetone. Acetone. All right, so this is just an exercise in the relationship between condensed structural formula, a molecular formula, and the structure composition. Let's take a look at what we have here. Maybe you can tell based on this tank, you know, what's the gas inside the balloon? What do you think? Helium. Helium gas, the element, most stable state gas, and it occurs as single atom particles. Helium gas. HE gas. B, do you know what that stuff is? The first time I saw that, I was thinking charcoal, you know, and so they're thinking carbon. I was thinking carbon, charcoal. But I was wrong. Do you know what that stuff is on the left there? That's lithium metal. Does that look like lithium metal to you? No. It doesn't look like lithium metal to me. And so, let's take a look at lithium metal. Or maybe, you know. This is what lithium. Lithium metal has this metallic appearance. There's a luster to it, you know. Although it corrodes rapidly. This is a surface that was just cut. Lithium is a soft metal. The bonds that hold the atoms together aren't that strong, so it can be cut, like sodium, metal, etc. But the problem with lithium is it's easy to corrode. And what you see here is just surface corrosion of lithium. And so whenever it's exposed to air, you know, this will discolor rapidly. You can already see it starting to discolor here, here, here. And so if it's a fresh surface, it's going to have this metallic luster. Oh, look, let's see these other images here. That looks like charred wood to me. Not really lithium. Again, not fresh surfaces. Look how much surface corrosion there is there. But here you can see some fresh lithium. Freshly cut lithium is going to look like this. Yes. More metallic nature. Well, anyway, that's lithium. Lithium, what kind of, does it form molecules, or what does lithium form? Does it form individual atoms? Or does it form a lattice? It forms a lattice. And so this is different. Even though we represent helium as He, which is accurate. I mean, it's just helium atoms, or He gas. You know, lithium we represent the same way, lithium, like that. But in this case, it's lithium metal, which is a solid. So we could call this lithium metal or solid lithium. Since it's a lattice, you know, we don't know it because there's no definite end. So the easiest is just to write, you know, the simplest unit. The simplest unit, later on we'll learn more, but we call that the empirical formula. Empirical just means it's the simplest. Okay. Then we go to hydrogen. We talked about hydrogen. Hydrogen, the most stable form of elemental hydrogen is H2, diatomic. hydrogen. Did they say diatomic hydrogen here? Just assume. It's a flammable gas, no smoking, no open flame. Do you need an open flame to ignite hydrogen? No, you don't need any flame. All you need is a hot surface. If the surface is hot enough, you're going to ignite hydrogen. So you got to avoid hot objects around hydrogen gas. All right, so that's a little bit about elements. Elements can be a little bit confusing, you know. So when I'm thinking about hydrogen in ethanol, for example, I'm not thinking H2, you know. Like this, it makes no sense to think in terms of H2 molecules in ethanol. It makes sense to think of hydrogen atoms. When I'm thinking about ethanol, do I think about, you know, how much diamond is in ethanol? You know, because there are 2 carbons there. And diamond is pure form of element carbon. No. Do I think of graphite in ethanol? No. I think of atoms of carbon in ethanol. That's it. Now, if I were to break this up, you know, if I were to take this and do some kind of chemical separation, you know, like whatever, electrolysis, although this wouldn't electrolyze that easily, but I do some chemical separation, I can separate the, you know, the constituents of ethanol into individual elements. And so I know that ethanol is made up of the elements carbon, hydrogen, oxygen. And so when I separate this, the oxygen would it stay as atoms of oxygen, or would it go to diatomic oxygen? It'd go to diatomic. The hydrogen would go to diatomic hydrogen, and the carbon would go to. It'd be nice if the carbon went to diamond, because then you know, I'd take the ethanol rather than drink it. I'd try to do some electrical or some other kind of chemical change to convert it into diamond, because that would be pretty nice, right? But most likely it's going to go to the most stable form of, you know what the most stable form of carbon is? It's not diamond. The most stable form of carbon is graphite. And so you'd end up forming graphite or something like that, or amorphous carbon. All right, so here's a little bit, the 7 diatomics, we already talked about those. You should have those memorized eventually. All right. Those are the elements. Now we're going to talk about compounds, naming compounds. And here it says compounds made from 2 nonmetals, but before that, I want to just talk about compounds in general. The nomenclature rules, the naming rules are going to depend on the type of compound. When we look at compounds, you know, we can classify compounds in different ways, and so. But all compounds share something in common. These are 2 or more elements chemically combined. 2 or more elements chemically combined. You know, they have some kind of bond. They're not physically combined. You know, like physically combined would be a mixture of hydrogen and oxygen gas. You know, you can have any ratio in that mixture, but a mixture of hydrogen and oxygen and water, those are chemically combined, and you can't have any ratio. And this chemically combined means they're bonded together. And so when we're looking at compounds, for nomenclature purposes, we separate into 2 kind of classes or more. We'll see. Nomenclature. The first type are what we call the molecular compounds. You know, compounds that form molecules. The molecular compounds are typically made up of nonmetals. Nonmetals. Typically nonmetals. So examples of this would be carbon monoxide, carbon dioxide, water. Yeah, carbon, oxygen, those are nonmetals. Let's see. Just in this yellow part of the periodic table. but not everything forms molecules in the yellow part. So for example, SiO2. SiO2, is it molecular? It turned out, well, let me rename this. SiO2 is called quartz. Does quartz form a lattice or does quartz form molecules? Quartz forms a lattice, and so this is not molecular, this is lattice. Versus ionic compound. Ionic compounds are typically metal and non-metal. So if we take a metal and non-metal, we'll get an ionic compound. An example would be NaCl. NaCl. And so this is metal and a non-metal, like NaCl, Na being the metal, Cl being the non-metal. CO2, this is non-metal and non-metal. But what is silicon? Is silicon a metal or a non-metal? Well, when we look at silicon, maybe let's not look at this periodic table. Let's look at another periodic table. The internet's there. Look at silicon. This one's kind of hard to see. Let's see. This one might be easier to see. When we look at silicon, do you see the zigzag line here? What does the zigzag line represent? The zigzag line represents the boundary between the non-metals and the metals. And so what if something lies right on the boundary? Do we call it a metal or a non-metal? Well, if it's on this side, we probably call it non-metal. If it's on this side, we call it metal. But the things that are on the border here are in this transition region. And being in this transition region means they have properties of both metals and non-metals. So we give them a special name. Do you know what that name is? The metalloids. So silicon's a metalloid. Although aluminum we definitely think of as being a metal, it does have some non-metallic type properties. So we'll talk about that later. So silicon being a metalloid, so it's kind of, I don't know, does it fall into this, where we have compounds that are typically made up of only non-metals, or does it fall into this, where we have a metal and non-metal? And so the nomenclature rules for this vary. And in fact, you see two names for this that are very common. If we consider this on this side, even though it's not molecular, it's a lattice, sometimes we call this, well, this is called what? CO2? Carbon dioxide. This would be called silicon dioxide, or quartz. Silicon dioxide. This is carbon monoxide. So over here, do we call this, let's say, would we call this sodium monochloride? Is this sodium monochloride? No, this is just sodium chloride. And so what we'll see here is this. This sometimes is called silicon, Roman numeral 4, chloride. Okay, so silicon 4 chloride. That's another name. And so the way we name this depends. on that, and since this is borderline, two names are often found for this: silicon dioxide or silicon fluoroxide. Sorry, not silicon fluoroxide. Let's see what time we got here. All right, so let's get into the names. Let's first look at these non-metal compounds. Non-metal compounds are typically molecular, but sometimes non-metals could be lattice. When we have lattice structures would be like ionic compounds or lattice structures. But this one's a lattice structure too. And so the question comes up, how do you know CO2 is molecular? How do you know SiO2 is a lattice? That's just kind of from observation, from memory. So, it's hard to predict. All right, so what we're going to do is we're going to go into the naming of molecular compounds, but we're not going to do all molecular compounds. We're just going to focus on binary molecular compounds. So let's take a look at this PowerPoint here. Okay, these are the rules for naming binary molecular compounds. Now, what is binary? Binary just means two elements. And so these are compounds formed from two elements. Examples of binary would be H2O, would be binary, because we only have two elements, hydrogen and oxygen. CO2, binary. But what about this? CH3OH, methanol. Is that a binary molecular compound? No, this is what we call ternary. It's got three. And so the rules don't work for this. The rules fail. The rules only work for binary. What about SiO2? Is that a binary molecular compound? Well, I don't know. But I do know quartz. And if I had it memorized, I'd realize, hey, wait a minute, that is not a molecular compound. That is a lattice. But we could name it as a binary molecular compound because you can treat silicon as being a non-metal. It's right on the border. All right, when we have a binary molecular compound, then the name has two words. The first word is the element that appears first in the chemical formula. So here, what element appears first in the chemical formula? Hydrogen. We include a prefix if there's more than one. And the prefixes indicate the number. And so what are the prefixes that we include? The prefixes that we include are mono for one, like di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Okay, this is something you need to memorize as well. And also you need to start memorizing the prefixes or the base names for carbons. If you have one carbon, we call it, one carbon's called meth. And so one carbon alcohol is called methanol. Two carbon alcohol is called ethanol. A three carbon alcohol is called propanol. A four carbon alcohol is called butanol. Do you want 5 is? Okay, once we hit 5, then a 5 carbon alcohol is called pentanol, a 6 carbon hexanol, peptanol, octanol, nonanol, and decanol. And so it's just the first 4 that get different names. Meth, eth, prop, bute. As far as the prefixes go, it's mono, di, tri, tetra, and then the rest are the same. Penta, hexa, hepta, etc. Well, anyway, if we were to name H2O, H2O, using our rules, this is called dihydrogen. Dihydrogen. And then, let's go on with the rules here. The second word. The second word is the element that appears second, and what we do is we change the ending to I, and we include the prefix. So here, this is going to be dihydrogen. How many oxygens do we have? 1, so it's mono. And then it's oxygen, but what we do is we change the ending. We don't want to call it oxygen, so we're going to call it oxygenide, but oxygenide sounds funny, and so we're just going to call it oxide. And so it's dihydrogen monoxide. But this double vowel is kind of awkward. And so what happens is we often just eliminate one of those, so it's called dihydrogen monoxide. Dihydrogen monoxide, or DHMO for short. DHMO my understanding is DHMO has been banned in certain cities in California. Have you heard about that? DHMO has been banned. Well, I don't know if this is true. This is what I just remember somebody telling me, that DHMO was banned by some city in Northern California because, dihydrogen monoxide is also known as hydroxyl acid and is one of the major components of acid rain. And so if you were to name it as an acid, it would be called hydroxyl acid. It contributes to the greenhouse effect, may cause severe burns, contributes to the erosion of our natural landscape, accelerates corrosion and rusting of many metals, may cause electrical failures, has been found. In other words, it's toxic too. Obviously, it's toxic. And so somebody came up with this data sheet here for DHMO. What to do in an accidental release of DHMO and all this other stuff, emergency protocols and stuff. And so what I remember was that, maybe this is an urban myth, but I remember that some city council came up with a vote and voted to ban it. Did you hear that? DHMO ban. But I can't remember what city it was, so I was looking it up this morning, but I couldn't find it here. But, anyway. Will there be a break on the test? You can take a break before the test. But there will not be a break during the test. Because normally what happens is if there's a break during the test, those people are just going to Google search. There will be a break today, so let's take a break now. How about that?
Have you decided how many questions the test is going to be?
The test is going to be similar to the test, the practice test, in terms of number of questions. It's going to be 2 pages long.